This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So good morning, everybody, and welcome again to another guest lecture from Miles in construction history. Now, Miles traditionally at this point would take us through iron in the Industrial Revolution period mainly. But following some questions we've had before, we also asked Miles to give us a bit of a broader perspective on metals and the use of iron and other metals even before the Industrial Revolution. So as usual, this is chronologically very. So Miles, please start. You're ready to go.
Yes, okay. Now, last time I spoke to you, I got into big trouble with Giorgio because I didn't properly answer a question from Jack about the use of iron in classical and ancient architecture. And I'm going to go back to the beginning now and try and deal with that. But I want to be very sure that you'd understand that it wasn't a question of somebody discovering iron and then somebody saying, oh, great, we'll now make some beams and trusses for our buildings. There's a big cultural change in understanding how metal can be used. When we talk about the Iron Age, we're talking about a cultural period, not just a technical period. I'm having some trouble here just getting this thing to change. Hang on. If you look at this table here, you'll see that across the world, copper and iron and bronze and so on came at different times at different dates. So, for example, in the Middle East, copper begins to be worked back before 4000 BC. It doesn't happen in Europe for about 2000 years later. So it's not a question like today when somebody invents a new vaccine and you all have to have it in 6 months' time, or someone in Silicon Valley develops a new app and we've all got it on our phones next year. These things spread in a very slow and cultural fashion, according to ethnic and political connections. Soft metals were known for a long time: copper, gold, lead, tin, not zinc, but those other metals, because they could be melted at a fairly low temperature and therefore could be extracted at a low temperature. But iron was not. The first big step forward was bronze, which is an alloy. I'll just go on to that there. First of all, copper. Here's a copper smelting site. Now, the point I want to make here is this is in the 3rd millennium BC. And although it seems to us primitive because they had no big crucibles and so on, it's actually a very big site. This is just a part of it. It reflects a great deal of social organization to be able to make this metal, even making copper. But the next step is making bronze. Now, bronze uses copper and tin, but it's harder than either of them. That's the benefit of it. So whereas copper could hardly be used for anything much in the way of tools, bronze could. Bronze could be used for tools and weapons. So the first thought somebody would have had was not to do with buildings, it was to do with how to improve the weaponry, maybe the jewelry, some utensils and so on. At first, it was not used for masonry construction except first of all, here's some examples of early bronze implements. The axes were probably not axes for wood cutting, but for weapons, for fighting, but a saw at the bottom. And here's where metal was first used in building. Stones were joined together by cramps, that is those double dovetail shapes, which at first were done in timber. You see here, there's a timber one at the top, and they sit into the recess there, so the stones couldn't pull apart. And around the timber was run lead, so you got a tight fitting. So in fact, the use of lead in the building was perhaps the pioneering use. And that's probably what gave rise to the idea of using bronze in these locations, because the timber cramp might then be replaced with a metal cramp, and it might have other shapes than that one we had. Here's a whole range of those used in Persia, or now Iran, under the Achaemenids. And there are many different ones used by the Greeks and the Romans and so on. But the principle of all of them was you have a recess cut into the two joining stones, you drop the cramp into it, and it stops them spreading apart. And you fit it tightly by running lead around it. So this is the idea people would have had about what metal was for. No idea about it being something you could use in tension or to beam or anything like that. It was only gradually that the implications arose. And bear in mind also that it was produced in very small quantities with great effort. So it wouldn't be obvious that you could use it in large structural elements, which is why this example here, put up by an archaeologist, is ridiculous. And I'm about to say you shouldn't believe it. This is supposed to be in the foundations of the Theban treasury at Delphi in Greece. The idea is that the recesses in the stone show that there were metal straps which ran in each direction and crossed at the corner, were halved into each other. Now, in fact, of course, you couldn't actually halve metal. You had no way of shaping the metal into the corner. It wasn't cast. It was a beaten rod in the first place, beaten by a blacksmith. Very, very difficult to form that recessed shape at the corner. But didn't have rolling mills or anything like modern production. To create a rod like that was a big effort, and there's no reason why they would do it. It wasn't necessary, and this really is a foolish proposal. And there are others, suppositions of that sort I won't go into now, which are equally unconvincing. The first one that is convincing is this one. This is the Propylaea at Athens. This is the gateway through which you enter the Acropolis at Athens and reach the Parthenon. It looks like perhaps like a Greek temple, but there's one big difference, if you can see it. I would remind you, don't hesitate to interrupt me if you want to ask questions or indeed ask me to slow down. What's all about this building in classical terms? It's that the columns aren't evenly spaced. Every Greek temple you look at almost has evenly spaced columns. This, because it's a gateway, has a wider space at the middle. That means that the stones spanning the space in the middle are under much greater stress because the bending moment is considerably increased by making it 1.5 times the size of the other column spacings. And what happens here seems to be rather critical. Now, bear in mind what we saw, to go back again, what we saw there was a reconstruction. The whole place was in ruins. It was rebuilt mostly in the early 20th century. So we don't know exactly which stones are right. You can't actually go to one stone and say this is how it was in this place. So there's been a certain amount of supposition about what went on here. Those are the stones were put back in place on this side, the inside face of the Propylaea. Now, what I believe it had was this, and this is my interpretation, varying from what the archaeologists said at the time, but it has been approved by Giorgio, so it's okay, you can believe it. Now, what you're looking at there is look at the right-hand side, the section, first of all. The beams are made up of 2 pieces of stone separately, in parallel, running across, and in the top of the stone is a groove, and dropped into that groove, that little black thing, is a bar of metal, quite a small bar of metal. Now, if you look at it in the elevation on the left, it's in that recess, and you might just notice that below the bar there's a space. So it's a little upstand at the end, and the bar rests on that little step. And that means that if the load on the bar makes it deflect at all, it still won't touch the stone. It'll keep the load quite separate from the stone below. Now, is that effective? Will that work? Will that help in the span? No comments? Well, it's surprisingly effective. What it does is this. It takes off, look at the bending moment diagram at the top. It takes off the top of the diagram. Makes a little beam, the little short beam takes the top bit, which this is a quarter point. We put the load at, divided into 4 along the length. But this is approximately true for whatever spacing you have. So in this case, it halves the maximum bending moment on the stone beam. Now, this is done intuitively. There's no way the Greeks could calculate that change, but it's obviously a very valuable device. Now, by and large, this wasn't taken up. There wasn't much use of iron for structural purposes for some time. But here is one little known example. This is a Roman one. This colonnade would have been all faced, you can see at the bottom right, faced with marble, looked like a marble classical colonnade. But in fact, underneath, it's flat brick arches. The marble's just a facing. And the flat brick arches have been held up with straps, which you can see at the corner, sort of hook it up to the end. And that's how it's able to stand up. And there are other examples in Roman times. This, in fact, is not iron but bronze, but in the famous Pantheon, in the portico, was this bronze framework, which has been removed since in the 17th century, so we don't know exactly how it was. It's not a truss, technically. It doesn't actually, it's not designed in the proper fashion of a truss, but it's a framework that works a bit in a truss-like fashion. And after that time, there were occasional examples in medieval and later architecture of iron being used in special ways like this. One is at the Hagia Sophia, the famous Hagia Sophia in Istanbul, which is of the 6th century. And it's here. Now, it's believed that these iron tie rods, you see the tie rod, say, across the bottom picture, running horizontally across the arch. It's believed that those are original. It's not all that clear. But one reason for believing it is that that exceeder, that curved arcade, would have exerted an outward force. Let me explain this. If you put a row of arches in a straight line, they push against each other, which is fine. If you have them in a curve like that, the resultant force pushes outwards. So that would tend to burst outwards, and this was held in by the iron rods. And there's a whole system of these iron rods right throughout this building, dozens and dozens of them, which seem to be original.
Excuse me, Mark.
Oh, yes.
I think like if the arch could like hold its own structural loads, why would they still need like this kind of like iron bars in between them?
I'm sorry, I'm not getting the sound very well. The arches.
I mean, like I said, like the arches, I think it can hold its like structural loads by itself as an arch.
The arch holds a structural load, provided it's contained at either side. So if the arch is not held at either side, it pushes outwards and breaks open. So if you've got a big massive wall or masonry, that's fine. Otherwise, you've got to have a tie rod across it. It spreads. You see what I mean? The arch collapses unless it's held in from the sides.
And this is a typical problem you have at the base of domes. Domes tend to burst at the base. They tend to spread, right? And so obviously, because of the curvature here, you don't have the counterbalancing effect of having another arch on the other side with a thrust that is equivalent of the arch that is in the middle, right? So Miles, you're saying here there was potentially, provided that that is the original, and that seems to be the case, these iron rods were used to contain the outward forces. Is that correct?
Yeah, absolutely. Just go back to the beginning. Think if you build an arch with little buildings, say child's building blocks. You build an arch out of those, and you'll find that the bottom pieces spread to either side. It just collapses unless you hold it in. See what I mean?
Yeah, okay.
Okay.
Thank you.
Now, all this changes really in Northern Europe in the late medieval period, probably mainly because there was plenty of timber, and so you could have the furnaces to make iron on a larger scale. And this is the first major development. What you had first was what were called bloomeries, little fires, where you heated the iron as much as you could, and you couldn't actually fully melt the ore, but you got a sort of spongy material out of it, and you could hammer it with a hammer and gradually force out the impurities and make iron. Very inefficient, made very small quantities. This development is the blast furnace, where you actually force a blast of air through the furnace and therefore achieve a greater heat. And because you achieve a greater heat, you can actually produce fully melted iron, and it's poured off and it becomes what's known as cast iron. What I have to do now is to explain to you a little bit more about the different sorts of iron. Cast iron is what you get straight away by that means, by melting down the iron ore, and it's not refined, it's got impurities in it, you see up to 4% of carbon and maybe all sorts of other elements, silicon and so on. It's poured into a mold, like pouring out a block of chocolate or something over, and it sets in the shape of the mold. It has a crystalline texture, and it's good in compression, but it's not good in tension. Which means it's not good in bending either, because bending involves tension. And it's also brittle. So if you have a fire in your building, it's made of cast iron, and you hose the water and change the temperature, suddenly the iron pieces will collapse. So that's cast iron, which is the basic form of iron, the basic cheap iron you get first of all. Wrought iron is where that iron is worked by a blacksmith or a rolling mill. So you hammer or roll the iron, and as you work the iron, it gets a fibrous texture. It becomes good in tension and good in bending. The only problem is it's much more subject to corrosion, to rusting, than cast iron. But wrought iron is much more general use for structural purposes. And then the third thing is steel, and steel really is a bit hard to define. It's more like wrought iron. It's hammered or rolled. It's good in tension and bending, but it's stronger than wrought iron. It's even more subject to rust. It involves various different additives, and steels were made by different recipes over time. I won't try to define those more precisely. But essentially, by the late 18th century, you could have cast iron, which was cheap, or wrought iron, which was expensive, and that's what was first introduced into buildings. And the buildings it was introduced into were two sorts, really. One was the factory, the first factories, and the other was iron bridges. And I want to turn to the factories first of all. The factory was a new idea, the heart of the Industrial Revolution. It was involved in the rise, especially of the cotton spinning industry and some other industries like flax. It involved the use of centralized power, the development of steam engines, but otherwise the use of natural water power. And they created special buildings in which to do this. Let me explain that for a start. Here's an early factory about 1800. In the past, people working in these industries, spinning and so on, would do it at home in their cottage. Somebody would bring the raw materials to them, and the whole family would work on it, and the products would be taken away, and they'd be paid. Now, when you're using a central source of power, in this case, you see at the bottom it's a water wheel, they have to be all in one place. So all the machinery works off that water wheel. The power from that wheel is taken up the building and runs into horizontal shafts on each floor, and each loom or spinning wheel works off that horizontal shaft. And so the whole basis of industry has been changed by this. Nail making continued separately, but other industries, generally speaking, went into these factories. Nail making was a bit later. Here's another one, and you can see here, you're looking at the bottom, the sections, you can see the water wheel, which operates the whole thing. And more clearly above, you can see the shafts which power the machinery above. The other thing you can see in this, if you look at the left-hand bottom section, is the arches in the roof. Now, the big issue here was fireproofing. Let me explain that for a start. Here's a sketch done at the time by one of these mills. And the arch there is of brick. See the middle sort of picture. There's a sort of shaded piece, which is an iron beam, sort of pointed bottom, and the arch rests on it. That's a cast iron beam, and the column below is a cast iron column, a hollow cast iron column. Now, what happens is that these factories were highly subject to fire. Just showing this because this is the picture we have of the grim Industrial Revolution. This is what they look like, although some of them actually were by quite enlightened employers. But this is one of the earliest big fires. This was a flour mill, but essentially a factory in London, the Albion Mills, owned by an architect, in fact, and it was burnt out completely. And in the year following that, about half a dozen factories and the mills in the north of England were also burnt out. So suddenly, fireproofing became the major issue in the design of factories. And that's what generates the developments in William Strutt's mills at Derby. There are three of them. This is the main Derby mill, not unlike the other ones we've just seen. In this case, there's a steam machine on at the bottom, where the boilers are in the bottom picture, the black shaded bit, but it's otherwise works in the same way as the water-operated factories. And here's his system. Now, again, you've got you've got a wooden beam here, but it's into an iron column. The wooden beam is totally surrounded so that no spark can get to it. So it's protected from the direct effect of fire. It's protected by having plaster on the bottom, by having brick arches running between the beams. That little timber fillet you can see there, the timber fillet provides the angle for the arch, but it's wrapped in iron. So even though it's timber, it's not directly accessible to fire. So the arches are built into there, and then it's filled with sand, and a brick or tile floor is put on top. All those things are tied together at the column. You see that iron sort of loop, strap which goes around the iron, holding it all together. And then the iron tie rod stops the arches from spreading. So once again, as I just described, these arches would have all been in a row, but there was only an ordinary wall at the end, so they would have actually flattened out and spread, and the whole building would have collapsed if it hadn't got that iron tie rod. The tie rod is the one element here, or two elements actually. The tie rod is of wrought iron, not cast iron. The other piece of wrought iron would be the sheet metal over the timber fillet. So all the big pieces are cast iron, but the small high performance pieces can be wrought iron. What's the problem in this system? Why is it not fully fireproof? I've got it all the time in the world.
Well, the road is exposed, isn't it? But
The rod is exposed. Yeah, but you're cheating. You know this, Giorgio.
Oh, okay. Sorry.
Yes, okay. Yes, that iron rod is exposed below the arches. Now, it's not so much that it'll burn, it's that it'll heat up, it'll expand, and as it expands, the arches will begin to sag a bit, the cracks will open up, the sand from above will pour through, sparks will get into the structure, and the whole thing will ultimately collapse. So that's the big point, the iron tie rod, which is exposed below the arch. Here's one of the developments of this factory system. Those are cast iron columns. This is a flax mill. An interesting point about this is you see the columns on the left, which had those big holes through the middle of the top. That's because that's where the driving rod, the shaft for the engine, passed through. The other columns are just ordinary structural columns. This was designed by Bage, who was a friend of Strutt, who designed the previous mills. There were 3 mills, which I showed you sort of in the diagram, a joint diagram of the system. But Bage designed this flax mill, and he made the beams now of iron as well as the columns. So the previous one had a wrapped up timber beam. This one has iron beams. And also Bage wrote a letter to Strutt setting out a sort of theory about the strength of cast iron columns. So he was beginning to take a sort of engineering approach to this. This Shrewsbury flax mill, which was finished in 1797, is the first known example of a complete iron frame building. Although, when I say that, the external walls are still masonry, so the iron frame is the whole internal structure. The external walls are the usual load-bearing brickwork. And the exposed tie rod, still, as you can see there, it still exists, so it's still a problem. This next example, the Salford Twist Mill, these are all up in the north of England. They're quite close together, around Manchester and so on. This has been, in some of your texts, still incorrectly identified as being the first example of the use of cast iron beams, which is not correct. It was built 4 years after that previous example. That mistake arose in the 19th century by the engineer William Fairbairn, and it's continued ever since, as I say, in some modern texts. But nevertheless, it's an interesting mill for other reasons. If you look at the section at the right, the beams aren't strictly parallel shape. They're not uniform shape. There's a rather odd system. There seems to be a change in profile, and in the middle span, there's see the black mark where the beams seem to join together. And here's what it was. So the beams are, in fact, 1.5 spans each, and they differ in depth as they cross. Why is this? It doesn't make sense. Well, if you take the beam over 1.5 spans, you're actually getting an improvement in the spanning capacity because it has a negative bending moment over the span. If you draw the bending moment diagram, you reduce the bending moment in the beam. So that's in a way quite a good thing. They've also got some sense of what the bending moment is doing because they've got a deeper beam, the beam deeper at the middle of the span. They haven't reacted to the negative bending moment at the column. So the other thing is that they incorporate into the beam itself the skewback, which is the element to support the brickwork. So you see at Shrewsbury, the one we just saw before, those beams had a sloping bottom. So where we previously in the first mills had a little bit of timber wrapped up in iron, the iron beam is now shaped so it can take the base of the brick arch. This next mill we're just looking at Salford, there was a little bit of that slope, but also a little flange. So the brick rests on the flange as well. But that was scrapped. In the end, they just used a sort of long T shape. So the brick relies upon the flange to support it. There you see the right what I was talking about in bending moment. The 1.5 spans, deflected shape, and the way the bending moment is something like halved by the use of that span system. Now, you're looking puzzled again? More worries about this? You understand it? Or? Yes?
I do, but
good. You know, yeah.
but can I ask a question at this point, Miles? To what extent these early examples of use of cast iron, right? Here's this cast iron or wrought iron?
Yes.
Cast iron. were driven by an understanding of structural stress, or were they somehow empirical?
It was entirely empirical. As I said, Baige began to try and develop some theory for the strength of cast iron columns, which is a pretty simple compression anyway. But the development of systems of analysis was mostly in the early 19th century, a bit after this.
Okay.
And so now taking it a bit even further, you see gradually from the top one is one we first saw, the timber beam, to the Shrewsbury one with the shaped flange, to the Salford one on the right-hand side, which has just the sort of T-shaped section, and so on. The other thing that's happening, if you look at these diagrams, is the dotted line, the broken line for the tie rods. By the time you get to the bottom one, the tie rod at Belper, the bottom, has been raised right up above the arch. And of course, that's to stop it being exposed to fire. There again is the evolution of those beams, more and more towards what we might regard today as being perhaps a more scientific I-beam. And here at the middle of the 19th century, the engineer William Fairbairn is showing his system. Now you can look at this and tell me straight away which elements are cast iron and which are wrought. The columns, are they cast or wrought iron?
Cast.
They're cast iron because you can't make wrought iron. You have to do a lot of work hammering the shape to make that shape. That's a shape you get by having a mold the right shape and pouring the iron in and casting it. But the beam above it, which is almost an I-beam, is rolled. So it's a wrought iron beam. And of course the tie rod, which is dotted in there, is wrought iron as well. You see it's just above the crown of the arch. So it's just concealed from fire. And that's the rationale. And above that, you've actually got a sort of concrete, not just sand, but sort of lime concrete above the brick arches and then the paving on top. Now, the other topic I wanted to mention was bridges.
Well, sorry, can I interrupt before you go on bridges? Just fascinating topic, by the way. Back on the previous example, so we start to see the development of the I-beam. But yeah, so this chart shows it very well. But am I right to interpret that fundamentally the I-beam seems to have, it was born out of the need to integrate cast iron with those brick arches or in mill factories. So it wasn't necessarily that conceptual ideal beam that we still use today, as the perfect shape. It seems like the form was evolving out of the need to integrate with bricks on the sides. Is that correct?
The T-beam was. The I-beam, of course, you don't need the top flange at all. We see the top right-hand side, Thomas Treadgold. He was one of the first people to conduct something like scientific experiments. So when he puts that flange at the top, he knows what he's doing. And the same at the bottom with the engineer Hodgkinson at the bottom centre and so on. They were now empirical but serious engineers analysing the stresses.
Yeah.
Now turning to bridges, there had been iron suspension bridges in China and so on, bridges based on chains, but essentially iron as a spanning material had not been used for bridges except in tension. This proposal here was not built, but this is in Scotland. The Inverary Bridge had been destroyed in a flood that would have been washed away. And as a replacement, the engineer, Robert Milne, proposed to put that iron, sort of a pair of iron arches across. So the stone abutments on either side and the pier in the middle remains from the old bridge. He just wanted to do an easy fix and put iron across to span it. It didn't, as I say, get built. But what's he trying to do? Why is the iron, for example, is that an appropriate structural form? The arch and the circle? No. Well, an iron arch is possible, not very logical, possible in wrought iron, but very bad in cast iron, because cast iron needs to be in direct compression, and the arch is not in direct compression. It's not a series of voussoirs, it's a bent piece of metal, and that's very bad in principle. And the same thing arises in the next bridge, but this is more complicated. Here, there'd been a need to build a bridge to support, in fact, largely the iron industry, the local iron industry at Coalbrookdale. And these are a series of designs by Shrewsbury architect T.F. Pritchard. Look at the top one first. That's just simply a timber bridge. So this is complicated, but it's a carpentry bridge. But it's his idea of how you make an arch bridge, because that's important, because it influences what he does when he makes a bridge of iron. The middle one is not really a bridge at all. It's a stone bridge, but it's showing the centering, the support for the bridge as you build it. So the black part is an temporary iron structure onto which you build the stone for that stone bridge on top. And you take the iron away after it. But while we have it there, I want you to look at the shape of the stone bridge. What's the point of the circles through it?
To reduce weight.
It is indeed to reduce weight, but also to some extent to reduce pressure on the bridge in flood, because if you have a flood in the river, it pushes those abutments. And if you have a hole through it, you can release some of that pressure. So it does both those things. I'm stressing this because these ideas from stone bridges and wooden bridges come to inform the first design of iron bridges, because people are traditionalists. They can't think of a new form straight away. Now, Pritchard at the bottom proposes quite a good bridge at the bottom. Although the bars are curved, they're not very heavily curved. He's obviously inspired by the timber bridge form at the top, but he didn't in the end get the job. It was passed on to another person. That's just a detail of those two bridges, so I'll move from there, who designed a much steeper arch bridge. Abraham Darby was one of the iron founders who were really the customers here who funded this bridge, and he designed that arch form at the top. So I'm comparing Pritchard's one at the bottom, which is quite logical, with Darby's one at the top, which is a very strange structure. You've got those heavily curved bars, a semicircular bridge, which is bad for a start. And there's those circles. Now the circles there, what sense do they make? They're not circles to release the pressure or substantially reduce the load. It's just out of the tradition of stone bridge building. All they do is help support the deck of the bridge at the top. This is a system of 5 arches, and you can see the section in the middle, 5 arches in parallel. They're made up of fairly small pieces which are then fitted together. You can't cast iron them in large sizes. That's the finished bridge. And although it suffered structural problems, it survives today. It's really the first proper iron bridge in the world, and it's of very great interest. There are details. Now a French engineer, a little bit later on, Rondelet, has proposed how to improve it. So the left-hand side is the bridge as designed and built. The right-hand side is Rondelet's proposal to improve it. And indeed, it is a much better design, a much more robust design. But it's later in date. He didn't do this at the same time. It's 20 or 30 years later. So there's the finished Coalbrookdale Iron Bridge. And there's a detail. You can see these funny pieces that are kind of cast iron, which are sort of bolted and fitted together. Very sort of fragile in principle. And this is the first of the compression arch bridges. Here now, Bicrotos is a fantastic design, much, much better, and not much later in France. Unfortunately, not built. This was a generic design, so you could use this design to build a bridge of any size. And in fact, a bridge something like this was begun in a builder's yard in Lyon, but never finished. But the French had a much better intuitive understanding of iron construction than the British, but they didn't have the industrial muscle to produce it. But that's the first of the iron voussoir bridges. Now the voussoir is in the stone arch, the wedge-shaped piece of stone which makes up the arch. An arch is made up of a number of these voussoirs, these blocks of tapered stone. And the iron bridges tend to do the same thing. So that last one we can see as being like if you made a number of blocks of stone into an arch. So those separate units are like stone blocks in principle. I now turn to some others. This one here is a rather marginal example. This is done by Tom Paine, who was the famous American radical who wrote The Rights of Man, was involved in the American Revolution and the French Revolution, but also had this interest in bridges. And he proposed to build this bridge at Sunderland in northern England over the River Wear. Now it's a cast iron bridge with curved bars, but because they're all joined together, it's not such a problem as the Coalbrookdale Bridge we saw before. It's a bit more rational. And in fact, it may not all be cast iron. It seems that some of this might have been wrought iron, and I'll tell you why in a moment. This, though, is a bit more of a joke, really. This is done by the engineer, by the architect, rather, John Nash, for a private property. And you can see it's meant to be a cast iron bridge for sure, but it's a rather quaint structure. And in fact, a few hours after it was built, it collapsed, although it did get rebuilt later on. But Nash claimed to be the inventor of the voussoir principle, not exactly in this bridge, but in other ones later on. He proposed cast iron boxes filled with concrete to be made into bridges. Here now is the site where Payne at first proposed the bridge I just mentioned. That is the one we saw with the curved bars and the little connections between them. He didn't get the job. It was built by a local, well, actually it's a local politician who funded the bridge and designed it, Roland Burden. And it brings up a couple of other practical points about this. These bridges were over rivers, and rivers were the main commercial connections through Britain. There were no railways, and the roads were poor. Goods travelled by water if possible, either on the rivers or on canals which were built for the purpose. So whenever you built a bridge on a major waterway, you had to allow enough height for the shipping to pass beneath it. If you're in a port, it had to be for sailing ships. Inland, not so much. This is designed to be built off those two sort of trestle structures rather than block the whole river so you couldn't sail through, and to have it high enough so the shipping could pass beneath it. And what they've built on top of that formwork on the top is a quite an elegant arch made up of separate cast iron units. So it is a voussoir bridge, it's like a stone bridge, but made up of hollow sort of units of cast iron. And they're made like this. They're a sort of cast iron grill, bolted together with cross rods, but the black pieces in the foreground run through the channel, link it all together. They're wrought iron. And it's thought that the wrought iron you're seeing there may have been the wrought iron intended for Payne's original bridge design, which is why we think Payne's design might have been wrought iron, because the components seem to be used here in this final bridge. So all those, each one makes something like a sort of open block, and it works like a block in a timber, like a voussoir in a stone bridge. There you see the 6 arches made of those at the bottom, and above them, once again, these circles, which make, again, no particular sense. They're just a traditional form. There's the finished bridge, very elegant, very successful, although it did have structural problems and had to be partly bolstered up in the mid-19th century. But not entirely rational still with those circles. And the French engineer I mentioned before, Rondelet, does the same thing again. You see on the left, the bridge as designed by Roland Burden, and on the right, Rondelet's proposal to improve it, which is indeed a sensible way to do it. And in France, you begin to get engineers doing something of this sort. This is the Austerlitz Bridge in Paris of 1806. Now, it doesn't have the circles. It has a complete grill, which is the logical way of using iron. You've got to have some infill there to carry the deck on top, but this is a simple system, largely in compression, which will do the job. Now, a different topic. I mentioned the canals. The canals gave rise to the need for aqueducts. That is to say, to carry the water across valleys. The idea of a canal is you want to transport your goods as near as possible horizontally across the country. So you had to make tunnels where you needed to and make bridges where you needed to keep the canal horizontal. If you couldn't do that, you had to have a system of locks where you changed the water level, and boats had to be floated up to the top and floated down again with great labour. So there's a great incentive to make a canal horizontal. And some of these designs were cast iron. This one, by the engineer Fulton, was one of them. Now, first of all, he's got arches below, which now we understand it's totally illogical, having quite a heavy load now with curved cast iron ribs, doesn't make much sense. Secondly, why has he got that large sort of walkway on the side? Isn't that a bit extravagant? What do you need that for? You know how canals work. They're barges full of raw materials or goods which go right across the country, and they're not worked by a motorboat, they're not worked by steam, they're worked by what?
To pull the boat through.
Yeah, they're pulled by horses, and that's the tow path on the left on which the horses walk, so it's a critical part of the design. Now here is the engineer Thomas Telford proposing an improved design. So he hasn't any longer got the curved arches. He's got props. This is now what we might now perhaps call a prop beam. But it's not quite as simple as first appears. It has the towpath again. That's the shallower part in the foreground. Oh, sorry, I'm just going again. There's his drawing there at the bottom. And he saw this as a new invention. He described this as a, let me find the words. I can't. He described it as a new principle he developed, which is trying to get adopted for other engineers. A principle entirely new, which I'm endeavouring to establish with regard to the application of iron. So somewhere in this design, he thinks he's invented something rather important. What it is he thinks he's developed a flat arch. You see the way those pieces are joined together, plates joined together, say in the top picture, with sloping joints. That's like a flat arch in masonry, in brick or stone, which is a valid structural form. Does this make sense? Is it a good idea? You think so? Well, not really, because once these are bolted together, it becomes a continuous beam. So it's in fact a continuous cast iron beam, which is not really a good principle at all. Bolting it together probably weakens it. So Telford was mistaken. But Telford is nevertheless one of the most advanced engineers of his time. He does some of the best designs of, especially of bridges. That's a close view of that. And here now is a much larger scale one. That previous one, the Longden Aqueduct, was more or less a dress rehearsal for this, which is a wonderful structure in Wales. So there's the towpath on the left and the canal on the right. And there's the system. Now, it looks as though you've got this supported on sort of solid cast iron arches, but that's just cladding. The bottom part, the sheets and the spandrel of the arch are just facing. And the system inside is again arched ribs, which doesn't make all that much sense still. So it's just like that, but with cladding over the outside. See on the right, you can look inside it. You can see the hollow structure of the arches. But Telford went on to design a number of true arches of very great importance. This is one of them. He proposed to build a new London Bridge in 1801, rather like the French design we saw before, on a huge scale. And again, you can see it's designed to pass above the height of the mast of the shipping. That's the reason for its height. And this was actually begun, work was begun on the banks on either side for the abutments, but in the end, for financial and other reasons, it was abandoned. So it's just a beautiful idea that never got carried out. He did, though, build a number of much smaller structures, which were quite rational. And this is typical. So you've got the iron arch itself, which has got sort of like a crisscross girder, quite good in compression, very sensible. Then instead of having the circles above, just again crisscross cast iron elements, which are economical and sensible for supporting the deck off the top of the bridge. And he built a number of bridges on essentially this sort of model. This is the Craigellachie Bridge in Scotland. And some interesting points arose here. It's assembled again out of cast iron, and you can see below the detail of it. And he raises some issues in writing about it at the time. He makes the point that you should, doing this, have all the elements of the same thickness. Why is that important? So all those bars, he thinks, should be the same thickness. Any reason for that?
Like same structural load?
Sorry?
So like, does that mean like same structural load, like there's some sort of like even structural load or something?
Not so much the load, no. It's because these are cast iron, and if you put it together and you have different thicknesses, after it's cast, it's hot and it shrinks. And as it shrinks, it cools. If it's different thicknesses, it cools at different rates. So the casting ends up with stresses in it. That's the reason for that. Quite sensible, in fact. And so he criticises other designers who use bars of different thicknesses. He also criticises the use of rings in the spandrels. He's the first person to say those circles we saw in the spandrel of the bridge are illogical. You could tell that they were structurally wrong. Here's a bridge, not by himself, but by one of his disciples, but a beautiful pedestrian bridge in Dublin, very elegant. And here, same principles on much, much larger scale is proposed bridge over the Menai Straits in Wales. The Menai Straits were one of the major engineering challenges of the time, at first for roads and later on for railways. Now, Telford, as I say, didn't get to build this bridge, but he did propose how to build it. He proposed to do this. Take the bottom right-hand side, you've got that abutment where he's gradually hoisting out sections, one after another, supported by cables until they meet at the middle and you've got a complete self-sufficient arch. Very ingenious. Does it make sense? Could you do this? Well, I hope you could, because it was done here at Hell's Gate Bridge in New York, and it was done for Sydney Harbour Bridge in Australia. So he was on the money there in developing that system. I now want to turn to suspension bridges, which rely, of course, not on compression, but upon tension. And of course, a very big change in principle. What does that mean in terms of the material for a start? The material of the bridge. You're never going to make it. No, I'm not going to use cast iron for a suspension bridge. That's the point. It's no good in tension. So you have to use wrought iron. So it means you're using a more expensive material, but usually using much, much less of it. So it may be economically possible to do it. So they're the two principles. The compression arch, of course, exerts a force on the abutments. It has to be held in. If it can spread, it's no good. The suspension bridge has to be tied in at the abutments, anchored in on either side. Here's an early example of this. I'm showing this one because it's actually rather, those arches at the end, those quadrants at the end, are rather like what Telford was proposing for his erection of the Menai Bridge. This is designed as a permanent way of taking the tension of the cable down into an anchorage at the end without taking it right out to either side. So it can be anchored straight into the stern abutments below. This is the first one proposed in England by Captain Samuel Brown. Now, Brown had been involved, he was a naval officer, he'd been involved in the design of cable structures, he'd been involved in rigging of ships and so on. So he was an early pioneer in this method. He didn't get to build this first. The first one was built, in fact, by Telford, and this is it. So here I'm back at the Menai Straits where Telford had proposed his arch bridge, but wasn't allowed to build it, so he builds instead a suspension bridge. This is now a huge structure, carries us by wrought iron, as I say, but by a sort of wrought iron chain system. Huge links in the chain. Now, these are not made in one piece. They actually, each of those bars is 16 square bars put together, bound by wire and then partly welded together, hammered together and so on, to make these giant links, which are the tension elements in the chain. Some details on them. Here's a French one, not long after, 1839. Now, with a cable. Now, the French tend to use cable. There's cable, iron wire, assembled together like rope into large cables, whereas the English tend to use chains early on. Here's a chain bridge on the English model in Russia. Now, the last category in this group is the self-contained span. So we've had the compression arch, the tension bridge, but this is just like a beam where you have a simple piece that runs across and doesn't exert either tension or compression on the abutments. That's the difference in principle. So they're the three diagrams. The bottom one is just a simple beam, but it may be all sorts of different shapes to get that beam effect. But the point about it is you can pick it up and put it down. You don't have to rely upon anchorage or support at either end of the bridge. It doesn't come early on. The idea of a simple beam is not at all obvious to engineers. Why is that? Well, the only large-scale beam you could make would be cast iron, and cast iron is not good in bending, so it wasn't an obvious solution for bridges at first sight. The first bridge of this sort is, in fact, a very odd structure. It's built over one of the first railway lines by the engineer George Stephenson, who was mainly a railway engineer. He was the inventor of the rocket, the famous first locomotive. And this is his bridge over a small local river, the Gauntlet. And here it is in the York Railway Museum today. It consists of a series of downward arches, downward cables, I suppose. They're made of wrought iron. Cast iron things like balusters, like the baluster of a staircase, in compression running upwards to support the deck of the bridge, which makes a sort of sense. But very surprisingly, there's another upward arch, which is also wrought iron. Does that make any sense? Let me just go over here. Here's what you're seeing. What would be the point of having the upward arch in that system? So the downward arch is simply tension, and the verticals carry the deck on top of the bridge. That makes sense. The upward arch does nothing. Well, with railways, you're dealing with a particular problem. Railway engine is a large moving load. You're not looking at a beam with a simple span of load in the middle. The load is moving across. When the train goes from one span to the next, the first span goes in negative bending moment. So that arch will resist the negative bending moment. Not that Stephen can analyse that in a degree of sophistication, but that's what it, I believe, does. It supports that arch when the train's on the next, when the locomotive's on the next span. Now, when you put all this together, especially with a giant piece of timber on top, it really becomes, in effect, a single beam. So that theory probably doesn't really have much application. But I think it's the idea behind it. And then, a more sophisticated form of the same sort of idea is Robert Stephenson, the son of the engineer George Stephenson, himself a prominent engineer, does the high-level bridge at Newcastle in northern England. It's a bridge which has a level for the roadway at the bottom and the railway at the top. It's a two-level bridge. Now, how does this work? The arches, they're going to push out at the end of the bridge. They're not going to push out at the end of the bridge, because each arch is tied. It's tied in what's called the bowstring fashion. So each arch is separate. You could take one of that arch and replace it without the bridge collapsing, the form of them. But you can see rather the same way the vertical elements are like balusters. They're cast iron. They're there just to carry the vertical load. The arch itself is now wrought iron, and the tie element across the bottom, which you can't really make out there, is wrought iron as well. And then you get to a true beam here with the Britannia Bridge in Wales. Now, instead of having all those funny arches and ties, the whole bridge is made like a beam, like a box beam here. And it's by the same engineer, Robert Stephenson. It's what's called a tubular bridge. It's so big that the trains go through the middle of this solid beam. And there it is. It was demolished only in fairly modern times. Extraordinary structure. The question is, how do you build a thing like this? How do you get that into place? First of all, the benefit of that tubular beam across a number of spans is you get continuity, which reduces the bending moment. So you get the top diagram. If you put each beam up separately, each section of the bridge up separately, as separate beams, you get the bottom. So you're losing all that benefit. So how can you get the benefit of the continuous beam at the top? By assembling these separate beams as at the bottom. It was done with great ingenuity. That's the question I'm asking, sorry. What Stephenson did was to put, say, the beam from C to B in first. It begins to deflect. He works out the slight angle at the end, joins the next beam on at that angle, and then lets it rest down. And then at the end, he does the next one, ED, the same way. So each one's joined on, taking account of the existing deflection of the previous beam. And it becomes, in effect, a continuous beam. It takes up the shape it would have if it was made in one piece first and then all put on at once. Very clever. Too complicated?
Yes, Miles, on this point, so was there a connection at that point? So say,
oh yes, once they're up, they're bolted together solidly. Yes,
they're bolted together.
Absolutely essential. It becomes a continuous beam. Yeah.
So the advantage here is, rather than installing each single tube separately, they would bend. Yeah. He would then let one first bend and then join according to that. And
But
also,
you couldn't make the whole thing, and
Yeah.
they floated out on punts, and each one was hoisted up by derricks and so on into place.
Yeah.
And so you had to artificially create that continuity.
And also, you mentioned about the construction process. Now, this is in the Menai Straits, right? Also, like the example from Telford before. So the issue here was also not being able, obviously, to put scaffolds to support these beams. And so there was a very ingenious process of erection of these tubes, right? By barges.
We saw, I think previously, hang on. Oh, sorry.
Yep.
You see there at the bottom, the tube is there being taken out on floats and punts, and then it'll be hoisted up.
And initially, there was an intention, if I remember correctly, for this beam to also have suspension cables that probably picking up these tubes at mid-span. Is that right?
Not that I know of, no. What I would say, the previous design, though, of course, for this site was that suspension bridge.
Yeah.
I didn't mention there that the problem with the railways with the moving engine, when they proposed to take the trains across on the suspension bridge, they decided they were going to unhook the carriages, take the locomotive across, take the carriages across drawn by horses, and then join them up again at the other end to deal with this problem of the moving load. With the tubular bridge, of course, it's not a problem at all. It's a continuous solid beam, and the railway can go straight through without any issue. So now there's a summary of what's been going on here, the comparison of those various bridges I've been looking at. Now to turn to the truss, which is quite a novel idea, and means going back in time to Palladio in Italy. Palladio is the first person who really illustrates rational truss design, rational triangular trusses, I thought I talked about previously. This is his bridge over the Cismone. And I discussed before how this is made up really in a logical fashion because the deck of the bridge has cross beams across it, so it's in 6 panels. Each beam rests upon this truss, and if you take the red shape, the paddle points support 2 of the cross beams, but there are others in between, and so you need to make a little truss in between to support the beam at midpoint. And so the whole thing is a little overlaid system of queen post and king post trusses, which is a totally logical response to the loading conditions. On the other hand, this one is not analysable in the same sort of way at all. This is an arch, much more like contemporary traditional bridge design, but perfectly sound nevertheless. And here's one in England, the so-called mathematical bridge, which reflects that level of understanding. It's really advanced carpentry, but not scientific design. Here now is a bridge in Switzerland. You can't make it out very clearly, but it has now within it arches of laminated timber, which slightly later but inserted into this bridge. There you see there. Now see the principle there. We've talked about laminated timber, and here it is physically laminated, not of course steam bent or anything, but just joined together to make the arch, bent in parallel to make the arch. And then by the late 18th century, massively complicated pieces of carpentry, but again, not scientifically designed as such. Here, lamination in which you've got keys joining the pieces together. I won't go back over all this stuff. But the point I would make is in North America, the rivers were very wide and there's floating ice. So in North America, there's great incentive to build large span bridges, which wouldn't interfere with the ice. Therefore, you get very advanced carpentry in those North American bridges, especially by this man, Timothy Palmer. And then you get attempts to make trusses to deal with this problem. Now, this one here is a very small scale truss I'm going to introduce you here. This is in a house, the Governor Thomas Bibb House in Huntsville, Alabama. And the roof trusses have been placed, instead of having a truss across the roof, there are parallel trusses like girders along the roof so that you can get a room in the roof space without being interrupted. So there are parallel cords there, and they're made up of timber. There they are. They're simply fairly crudely sawn timber, nailed into place. And this is the invention of the architect of this house, Ifield Town. It's called the Town Truss as a result. This is a good system. Will it work? And if so, why wouldn't it have been done before? Well, it does certainly works. The reason it hadn't been done before is it involves a large amount of sawn timber and a very large amount of fixings. And what's happened in North America is they've developed sawmills, so timber is much cheaper to saw than it was, and they've developed nails, and that number of joints is no longer a big problem. And that's the basis for this technical development. Anyway, the Tyne Truss now is used quite widely in bridges. That's in North America, you get these covered bridges. That's a bridge with the roof on because of the snow. Pretty North American thing. That's a version of the Tyne Truss. This one again. And this one now in Russia, done by an American contractor. And then they turn them into iron, mostly wrought iron.
And this obviously works well also with the problem you described before, Miles, about the loads of trains moving as a movable load over the bridge that shifts continuously the point of maximum.
Yeah, exactly the same thing, the same, almost like a beam, the same sort of thing. Yeah. Now fully wrought iron in America. The hard truss is a bit different. The hard truss is more scientifically designed. It's a crisscross design, and you've got vertical elements which are wrought iron, and the crisscross elements are, at first, timber compression members. Now, it might seem at first a bit illogical, but it does work, especially it works when the loading is variable, as we're just talking about. The loading, if the train goes across, is not at the centre, it's somewhere to one end or the other, and therefore these uniform panels work fairly well in dealing with that. So if you had a simple load at the centre, you'd change that truss to what I've shown at the bottom. You take out all the extra members. It's only because you might have an asymmetrical loading condition that it's worth having the complete truss design at the top. But looking at the bottom, you can see how it actually works. You've got the compression member, then the tension member hanging down, in effect, sort of, how to describe this simply. Well, you can see how it works anyway. The verticals are in tension, the diagonals are in compression. And here's one which was built near Melbourne very early on in 1853, that system. Here's now one which has been done not in timber at all, but all in iron. Now you have to come down to the point, in these trusses, sometimes you can't tell which members are supposed to be compression and which are tension. And especially if you make this bridge in iron, are the verticals in tension or the diagonals in tension? So you may not know, but here's another one near Melbourne in the late 19th century on that iron system. That actually, I should have said that's a Pratt truss, that with the reverse system. And there's some other mad sort of ones. Here's Pratt. He's now got the verticals in compression and the diagonals in tension. So he's reversed the one we saw before, the hard truss. So we start with the Tyne truss at the top, the hard truss, then the Pratt truss, all slightly different in principle. This one here is odd because you see the diagonals are sort of, there's a half diagonal in one panel. There it is there. The Americans just experiment with all sorts of different systems. When you get to the Whipple truss at the bottom, it makes sense, but you can't analyse it. You've got too many tension elements in it. It makes sense, especially for railways, because it can support a load at any part of the span. But it's a redundant truss in design terms. There's an example of one of these. The middle is a rotating span, because that's, of course, for the shipping to get through. So commonly in these big bridges, you have to have a span which revolves the middle to open like a gate. And then the Bollman truss. Now, I want you to look at this truss and say, what is actually taking the load? What you really have there is the crisscross pattern, which is like a Pratt truss. But underneath it, you've got those raking tension cords from either end, like a sort of cable stayed system, sort of suspension system, you've really got two complete bridges, one on top of the other. So which one's going to take the load? Both. It's an irrational design. If you had to take a guess, how's it going to work? Well, I'll suggest you, if you built those two bridges separately, and you put the same load on both of them, which one would deflect most? Well, I'd say the suspension one will deflect most. Won't fail, but it'll deflect most. That means that if you put them together, the load will fall first of all onto the other bridge. So the suspension one will get out of the way, if you like, and the load will fall onto the Pratt truss behind it. So there's a Bollmann truss in practice. There's my analysis of it, as described to you. You've got the red suspension structure, the blue compression structure, and it's the blue one which will take the load first of all. And this completely mad system, I can't explain it. It's what the Americans were like. And this one, which has a sort of rationale. So what we're looking at here, how does this work? This is the compensating truss. You've got two arches you can see. If you took those away, in effect, the rest of the structure is also like an arch, in the sense that if you put a load on it, it will push outwards on the abutments. So it's really like three arches overlaid. Who knows which one will take the load? And then this seems even madder, the spider web of stuff. The Fink truss, so-called. Is it mad? It's actually precisely the same logic as the way I analysed Palladio's truss before. You've got a big span, which is trussed up from the bottom of the top diagram, so it supports the centre of the truss, but the loads are coming down on the cross beams where the black arrows are. So you've got to have another little truss to support the sort of third point load. And then within that, another little truss to support the next one. So what you've got is a quite logical structure, and you can analyse the stress in each separate member quite clearly. So it's actually quite a good system. And there's an example of this in a bridge in Australia, in Queensland. And one which used to be in Collingwood, Melbourne. Now, the final example here is the Warren girder, which is a sort of much more rational girder in our terms. What happened was about the middle of the century, two engineers worked out how to analyse the stress, analyse the stresses in parallel chorded girders. So you had a sort of scientific basis for working out the load in a girder. One of them was Kennard, who designed this bridge, and the other was a Russian engineer about the same time. This is the Crumlin Viaduct, which is this bridge in question. It's in Wales. It's a viaduct for taking a railway line across a big valley. And the important point is at the top of the picture, the zigzag truss. So there's no vertical members in it. They're 60-degree members, and it's totally reversible. So you can put that upside down to be the same truss. So you still get trusses. You can buy trusses like that from a supplier today to make your own garage at home. It's a very efficient system. Now to turn back to conventional building. First of all, the I-beam we talked about before, how you produce those shapes. The ones we saw before were cast iron beams. We can just make any shape you like in casting. But to make a wrought iron beam on a large scale is quite difficult. Here's one way it was being done. A number of separate bars of wrought iron on the left are put together and then rolled steadily with a series of rolls until you got to the shape finally on the right-hand side. Quite a laborious system done in the 1860s. Here now is a series of rollers done for this purpose, starting at the top left and getting in at the bottom right. One roller at the bottom right is working inside the other, as it were. So you've got two rollers, both of which are being worked by machinery, but you can have one which turns by machinery and the other just follows. You just put the roller in place and it'll just turn automatically.
Miles, here we're talking about wrought iron I-beams, right?
These are wrought iron. I'm saying we've got wrought iron, yes.
Which incidentally, the process is still the same, rolling for steel in principle.
Same thing, we'll come to steel soon, yes, it's the same thing for steel essentially.
Yeah.
Here's one of the first deliberate uses of an iron beam in the Palmstove at Kew outside London, which is a big greenhouse. Unfortunately, it was destroyed in a sort of hurricane in England about 20 years ago, and most of it has been replaced. But the beams, the arch members were in fact I section members, and the engineer, Dismas Burton, was quite knowledgeable. It was done on purpose. And what happened there, in fact, was that it first been proposed to build this in cast iron, and Burton proposed to use wrought iron at much greater expense, but more durable, much lighter and more durable, and was allowed to do it. Here now are beams being rolled in France on the left, and then built up on the right. So this is a much easier way of making an iron, an I-shaped beam. You have a flat piece of iron and 4 angles, which are then bolted together to make the I shape. For a long time, all the larger beams were made by this process of building up, assembling components together, first by bolting, later on by riveting, and in due course by welding into homogeneous beams. Here are some of the rolled joists available in England in the 1850s. And now I'm turning back to the United States, where...
Sorry, Miles, sorry to interrupt, but back to the I-beam. So at what time do we find the use of the I-beam in a self-aware way of the I-beam as a structural member that resists, compression and tension?
Well, really, here in this building, I'm just about to turn to, in fact.
Oh, okay, sorry.
Yeah, that's fair enough. I mean, I don't mean they could necessarily calculate it accurately, but they certainly understood the way it functioned structurally. This is the Harper Brothers building in New York. It's the great publishers, and the facade is largely cast iron, but it's what I'm turning to. It had a system a bit like this one, which is contemporary. Still, the columns are cast iron, which is quite logical. It's only taking compression. But the beams, you see, the large beam to the left is a rolled beam, then a smaller rolled beam the other way, and then again fireproof flooring with the bricks forming an arch between the secondary beams. Here now again the use of built-up members. So you've got a rolled beam for the small section at the top left, but everything else is built up with bolts. And this becomes typical construction through the rest of the 19th century. Cast iron columns remain for a surprisingly long time in quite major buildings, even skyscrapers. But wrought iron very quickly takes over for all bending members, for all beams and girders. The other element here is what's called the crush box, where you join the beam together. It's a complicated joint. So a special little cast iron section is made into which everything fits. So you can transfer the loads from the beams to the columns. Here are standard forms of built-up girders, still being used into the 1920s in this case. As I said before, you might have joined those with bolts first, then rivets, then welding, all the same. And then you get shapes, even hollow shapes, made by the same process. This is the French architect Eugène Emmanuel Viollet-le-Duc, and this is very much like what standard construction would be in the 1880s to say 1900 or so in Europe. Here are in Australia, the same thing exactly. Now I want to turn to these wrought iron trusses in buildings, not in bridges. Quite early on, the English realised that you could make a lightweight roof using wrought iron, using almost entirely wrought iron. And this is an example in the Woolwich Naval Dockyard in England. Here's in America for the Capitol building. Now these might be made partly out of rods, but out of angles. In this case, they're angles and flats. This one here, a railway station, very large span railway station in England, 1868. So this is, in fact, got some cast iron in it. Which elements are cast iron? You can tell by looking at it.
Joining point.
You see my arrow when I move? Is it visible on your screen? No. You can't see my arrow yet. These elements
Okay.
here are cast iron, the struts in compression. Logically, a cast iron, you can tell because of this funny little band around the middle, which you wouldn't have in a rolled wrought iron section. So the short compression elements are cast iron, but otherwise the truss is made of wrought iron in tension. Some details. Not the same one, but similar. Now I want to introduce corrugated iron to you. Corrugated iron today to us seems to be sort of primitive material, but it's actually a very sophisticated and ingenious device. It was patented first of all. The idea of actually fluting iron, rolling it with the sort of corrugations was not novel. It's been done for small elements of various sorts. But to make it a structural material was a new invention in 1829. And this is Henry Robinson Palmer, the British engineer who took out the patent for it, and proposing to use it for the roofing of buildings for the first time. But also for fireproof doors, you see here, including that rolling door for a warehouse in the bottom. But most of all, Palmer uses it at the London docks to roof these large dock areas. So corrugated iron, if you picture a sheet of ordinary iron, flat sheet iron, lightweight iron, and you put it across a span, say between two chairs, and stand on it, it'll just collapse. Let's take the same sheet and you corrugate it, and it will take quite a load. If you corrugate it and then you arch it as well, it gets even stronger. It's a very, very strong way of using iron of a given thickness, so an ordinary sheet of iron. And that's what he's relying on here. It does rely, though, of course, being an arch, on being tied together. So you can see at the right-hand side the tie rod going to the wall. Not quite so clear, but again, there's a tie rod going right across the arch to hold it together. So once you've got that arch and the tie rod, you've got a very strong system. If you make a very big arch, you might have to put some more tension rods in between, a vertical rod in the middle, perhaps, say, and subsidiary tension rod. It's a great system. And Palmer sold his patent rights to a man called Walker, and they began to be promoted, this iron system began to be promoted mainly from 1843 onwards in Britain. Here are some of the forms of corrugated iron. It's like a sine curve mathematically, and mostly you don't get, say, the top one is a typical one. The next one, the deep one, is not at all common, but later on you get fireproof flooring made on those deep sections. And they even made aeroplanes out of it in Germany. In fact, if you watched the Battle of Britain on the television last night, you would have seen one of these corrugated iron German aeroplanes. But most of all, it's important in flooring. The idea of an arched iron floor, of course, we've seen, because you had the brick floors first of all, and then iron replaced the brick. Here's one example. James Naismith is using corrugated iron here in a rather odd fashion, because the corrugations are running across the arch, not along it, as it were. So it's not getting the benefit of that double curving. Here now is one of the corrugations running in the better direction in a Scottish building. So it's very strong, and you put concrete on top and it can't deform at all. It becomes enormously strong. In America, one company in particular had a patent system, which you see here. And I said you could get deeper forms of corrugated iron for fireproofing. This is a little known, but I think very interesting aspect of this. Heinle Mann and Company of Berlin developed this structural iron, first of all, but also for fireproofing systems. They took what would be ordinary corrugated iron, instead of a sine curve, they have a semicircle at the top, a semicircle at the bottom, and a straight section in between. So it becomes a very, very deep corrugation. And some of it's made very thick, the one in the middle, so it's a very, very strong element. And they use it to support floors. So no secondary structure at all, just the corrugated iron straight across, bit of concrete and wood on top, and you've got a complete floor. This is Traeger Wellblech, load-bearing iron, developed mainly in the 1870s by this German company. And it's interesting to me because it's virtually unknown in Britain and the United States, but it's known in Holland and Belgium and in Germany, and it's known in Australia because a German engineer introduced it into Australian buildings. And here, in a letter written by one of the people involved in the manufacture of this iron to the government, they're proposing to build a penitentiary, a prison at Kassel in Germany, using this heavy gauge iron now in an arched form. So it's really replicating what has gone early on in Britain, but now with this heavier iron. So in the left-hand side of the letter, he's done this sketch showing this system of fireproof construction they propose to build in the prison. This is the actual point, if you like, when this invention is made in Germany, in this letter, which I own. There it is. Sees Mark Traeger Wellblech, which is their iron. Unfortunately, they didn't get the job, so this prison wasn't built in their form. But here it is being used in Melbourne. See the arch iron at the back of the picture? That's this Traeger Wellblech iron. The concrete on top. Okay, well, the triumph of French engineering at the end of the 19th century was quite major, and mainly due to Gustave Eiffel. Gustave Eiffel, of course, you all know because of the Eiffel Tower, although really that was not designed by him himself, but by one of his staff. But he is nevertheless a very important engineer. Before he built his major bridges, the largest iron arch in Europe was the St Pancras Station arch in London, which had a span of 73 metres, and remained the largest for about a quarter of a century. But it's worth thinking about how it works. First of all, is it a true arch? And secondly, if it is a true arch, what stops it spreading?
Not a true arch.
Is it detail? Well, it's sort of not a true arch exactly, no, because it's got hinges in it. So you've got at the point at the top, that's a point where the members can actually rotate, and at the bottom also they could rotate, so there's actually 3 pins, 3 hinges. It's more like a sort of triangular structure in a way, it just happens to be curved. And how does it stop from spreading? The same issue still arises, however it's whatever form it takes, it has to be stopped from spreading. It's stopped from spreading by having horizontal members below the railway tracks at the bottom. If you make out at the bottom of that picture there, the horizontal beam right at the base, it goes below the track, so it's tied together as you might expect. Now, this, as I say, was the biggest arch for some time until Eiffel. It couldn't be analysed in detail, apart from the overall 3-pin form. You couldn't analyse the stress in any particular part of the arch. What Eiffel did was to make big arches which were not 3-pinned, but mostly 2-pinned. This one here, over the, well, first that one there's over the Douro to Porto. You can't see it clearly there, but I'm talking about the bottom arch, which is crescent shaped. Now, the crescent shape there is because it has a pin at either end, but it has bending moment within the arch. It's not a pure compression arch, and that builds up towards the centre. And if you go to the French example, the Viaduct Garabé, which is being built there, the same thing applies. This is a crescent shape. There's a pin at the bottom, but no pin at the centre. So the railway station had 3 pins, which means you could break it down completely. You could analyse at a large scale the forces in each major section of it. In this one, you can't. It's a compression arch, but contained at the bottom, and you can't work out the stresses within it. It was felt somehow to be more secure for railways and loads like that than having a 3-pin arch which could be analysed. That's why these ones were often built. But there's the finished structure, wonderful structure. And what's it made of?
Wrought iron.
Is it wrought iron? That's right, not steel. Eiffel didn't use steel, it was very conservative, he used wrought iron for some reason. Now, turning now to the 3-pin arch, here's an example in France, not by Eiffel, of course. This is the Galerie des Machines, the machinery hall for the Paris exhibition of 1889. And you can see there that the members are really separate members being hoisted up into place. and they have a hinge in the middle and a hinge at either side. There's the hinge at the bottom. It's important to make it work. So these are really quite designed to allow rotation for it to function in the way it's designed by an engineer to operate. And here's an example which is often attributed to Eiffel, but incorrectly so, in Chile, the central station at Santiago. And another one in Chile, same thing, 1905 to 12, a bit later on in date. And there are the bases of the two arches. Again, carefully designed to allow the free rotation at the base. An illustration of one at that time. Now, turning to steel. Steel so far has been quite widely used for quite exotic purposes, for various sorts of machinery and so on. Even cast steel, as opposed to rolled steel, was being used. But in structural terms, it was an expensive material, not introduced for until quite a late stage. Here's an example of steel. You can't tell the difference straight away, but in practical terms, often it has a rolling mark. So when you find a brand rolled into it, in this case it's saying Middlesbrough, that means it's usually steel, not wrought iron, because for some reason wrought iron was never rolled in that fashion with the brand in relief. Here's another example, a couple of examples of German steel. And here's the first really major structure using steel. This was the bridge over the Mississippi by the engineer James Eads, and he decided to use at first steel rather than cast iron because of the extent of the span and the loads involved. He couldn't get steel good enough at first, and work was suspended for a time. And finally, because he was using cast steel at first, finally he got steel made by the famous Carnegie Company in America, which would meet his tests, and work was resumed in 1868 using chrome steel for the first time, very expensive material. So this is, steel was the major part, but not the total part of this structure. The first all-steel bridge was also over the Mississippi River, so it was over the Missouri River in 1879. This one here, a very simple rational design by the Chicago and Alton Railroad Company. And this is the first use of rigid steel members as opposed to cables for a bridge in the United States. So quite an important development. The structural members here are actually tubular, they were hollow. And steel comes into use from now on in America, but only rather later on the continent of Europe and in Britain. The first British example of note is really quite an extraordinary one. It's the Firth of Forth Bridge in Scotland, which is huge, as I said. It uses open hearth mild steel made in Britain. It's much bigger than any of those bridges by Gustav Eiffel. It spans, the separate spans are 513 meters, 3 times as big as the Eiffel spans in Portugal and France. And it's designed again so as to provide headway for shipping. The reason for this rationale of this design is so that the midpoint of the span is lifted up high enough to provide the required height for the shipping to pass underneath. So what he's done is to make these great truss-like things which are sort of shouldered out, and a little beam hung on the end of it, a little short girder hung on the end of it across that high part of the span. You see there?
Miles, sorry, can I have a question?
Yeah.
Why does it need the support from top and bottom, both sides of support for this one?
I can't hear you terribly well. Why is it like what?
Sorry, why does this brake need support from both the bottom and top?
I still didn't hear properly, but let me just say they've designed this so that the major elements can get a cantilever out, and they don't have to build an arch across in a conventional way. And they've hung onto the end of that this little short beam to provide the clearance. Now, I don't think that's your question though. What you try and say it? I can't hear properly. So if Georgia can hear it and tell me.
Yeah, I think the question is, you answered. The question is why the deck is supported with members from the top and members from below. Obviously, yes, there is that span in the middle, which is shorter with that arch structure very shortly, and then a midspan. But then there's these cantilever sections that come from those struts that hit on the sides there of the river. Perhaps showing some pictures under construction work.
But just first, before I do that, this is not an arch at all. So the reason for the members on top is their intention. That's like a great sort of coat hanger structure. It's not like an arch bridge at all. So consider those as separate structures without the bit in between, little joining bit. They have tension in the top. So those members at the top perform a very major role. It's like, well, I can't describe it any more than that, really. There's the overall principle. And here's get the scale of the bridge. See the size of the train in the middle? These are just huge tubular elements. Needs under construction. So you can see you can build out from this very principle joining an arch together before it's finished. You can just build out from the center out to either side until you've gone as far as you want. And those top chords are very much in tension. Now, why this could be done is because they developed machine riveting, and those little platforms everywhere are where people were working to rivet the bridge together. This was a major development at the time. So you see in that diagram, all those dots, thousands and thousands of rivets are being used. They had mechanical drilling and mechanical riveting on a huge scale for the first time. Now, here's the same principle being used. You see, it's not the coating element is different, but the idea of having a little freestanding section on either end and then a little span in between is exactly the same in this bridge in America. It's a very lightweight bridge in America. Now turning to steel sections. Again, we talked about the rolling before of wrought iron, which is essentially the same problem, and that's how steel was being rolled to the left, from rough shape to final shape, with usually at first 2 active rollers and 2 passive rollers. So you might have a roller pushing in from either side, which is machine powered, and the roller at either end, if you like, at the top and bottom of that view there, which is just moving as the steel pushes through. It doesn't require to be separately powered. If you look at the right-hand side, the attempt is being made now to roll a sharper section. Where the arrow is on the left, you can't get rid of that sort of tapering section in the simple rolling process. If you want to make a more rational section, which is more like a straight flange rather than a tapered one, you have to go to develop new means. This is one on the right is one means of doing it, the sack mill, which was never really a great success. You've got 2 shaded rollers, which are moving on the vertical pivot. See the axis running vertically. They're rotating on that. The sections in between them. And the 2 large rollers above and below are just moving with the momentum. They're just there to keep the thing in shape rather than move it forward. And a similar system was developed in the Gray Mill, which was the first effective way of rolling what are called universal sections which instead of being short flange like the left-hand one, are more like an H section. So you get things like this. So these Gray mills and sack mills produced these very sharp H-shaped sections, which you couldn't do by traditional processes. And then the joining together. I mentioned the bolting and riveting alternatives. Here's bolting being used in a trench building. Unusual because mostly you couldn't see this because fireproofing required it to be concealed, but in this case, for some reason, this was allowed to be seen. And here's a nice railway station terminal in America, United States, which again bolted together. But in the fourth bridge we just saw, all that was riveting, and there's some forms of rivets on the left. The rivets are quite a traditional way of joining things together, even joining leather together for shoes, for example. But the development of machine riveting in the 19th century, late 19th century, was a very major change, and it was the basis for many of the early skyscrapers in the United States. So welding fuses the metal together. You melt enough of the metal together and maybe add metal to it to make it a homogeneous section. And it can be done either by using those gases to reach the temperature, or by electric arc. They're the two main sorts, oxy welding and arc welding. An example of an oxy welding apparatus. There's arc welding with an electrode. And here's the Empire State Building, New York, the great skyscraper, being done by arc welding. I want to turn to the portal frame, which is an odd irrational form of structure, which was became quite significant. First of all, going back in France to this exhibition building in Paris, not the one you saw before, but an earlier one. This is the Galerie des Machines at the 1878 exhibition. It's not a conventional arch system at all. How does this one work? What's the structure we're seeing here? Is it an arch? Post and beam? What is it?
Like a portal frame, but with trusses over an arch.
Yeah, what I'm getting at is it's a portal frame. That means that the columns are going into the ground and there's bending moment transferred into the ground. It's not a pin joint. So it's getting strength from the ground, and the bending moment is continuous right across the frame. It can't be analysed by ordinary simple engineering methods at all. It has to be analysed by models and so on. So this is an early example in France of what you call now a portal frame. And here's a portal frame in a skyscraper in America. The old Colony building in Chicago. In the cross section, you've got those where those arches are. There's a solid flange around the arch. So that's making this a rigid structure, a rigid frame structure. You probably want to go here, here's how it's built here. So in other words, there's no pin joints at all here. This is meant to be a completely continuous, rigid structure, at least in the major structural bays. The bits in between don't so much matter. And this relies, of course, upon a massive amount of bolted sections to do it. So it's a completely different attitude towards bending moment. And the bending moment tends to be greatest at the joints rather than at the center of the span. It reverses the normal conventions. There's an actual detail of one of those portal arches. Here's the same thing being done, but not with solid spandrels at the side, but with framing, but the same thing being done in Arthur Vierendale's structures in Belgium. And again, you see the girders and the columns don't have any diagonal elements at all. It relies upon the joint to make these rectangular panels. So this bridge, quite like any bridge you've seen before, you can see the flaring out of the joints reflects the fact that the bending moment is strongest and is greatest at those points. There's an analysis of it. No bending moment in the middle, the point of inflection in the middle, maximum bending moment at the joint. It doesn't make sense really in a way. It's extravagant material, but it produces a very nice modern looking structure. And also in some cases, it can function usefully where you need that space to be open for some functional reason. So here you see this is still an arch shape, but it's still a portal frame type structure because it has those rigid joints. And Vierendale built about 36 of these bridges on one canal in Belgium. That's the most famous collection of them. Here it is here. That's a beautiful one. Here's where it functions. This is an American factory, and because of there's no diagonals in the girders, they can take a conveyor belt through the middle of the girders through the factory. Turning to the skyscraper. The skyscraper is, of course, largely an American invention, although it has a certain amount of French input into it early on, with the Statue of Liberty, which you may not think of as a skyscraper, but it is. The Statue of Liberty was a present from France to the United States, and it was designed by a French sculptor with an Italian name, Bartholdi, and it has an iron structure within it. It's sheet metal on an armature of metal bars and so on, which is carried off a basic frame at the middle of it. You see there. So there's a sort of pylon up the middle, and then a frame built out to carry the outer face of the sculpture. And around about the same time, just coming ahead of myself, is this one in in Prague, 1891. Again, all made of wrought iron, not steel in this case, but again a complete skyscraper structure. There's a detail of that. Now in America, you have up till now higher and higher load-bearing brick buildings, especially in Chicago, big office buildings of load-bearing brick. They begin to introduce into them fireproof floors within the outside brick framing, but still with an outside wall of load-bearing brick. Looking at this floor here, these are built-up sections. At first in wrought iron, later on steel. There's very little change. Often don't know, but this is wrought iron here. And they're made fireproof by having around the column, you see this, look at the column at the bottom, that curved section is sort of pieces of extruded terracotta placed around the column and then plastered around so that there's a completely impervious surface and fire can't get into it. And then between the beams at the left-hand side, a tile arch, an extruded piece of terracotta which slots into the space between the beams, then again is plastered over the bottom, so none of the ironwork is exposed to fire. And here's what looks more and more like a modern piece of framing as a result of this development. And this is the point where wrought iron gives way to steel in the, especially the home insurance building by William LeBaron Jenney, who was the pioneer of skyscraper construction in America. Now here now is, oh, here, sorry. I have water here. Lost the slide. Okay. Oh, I might come to later on. What I was about to say is the highest of these buildings, and the one I had in mind is the Monadnock block, was load-bearing brick to like 17 stories high. The wall at the bottom was over 2 meters thick at the bottom. That meant that you had windows like tunnels. You could hardly get the light into the bottom of the building. And also a very large part of the floor area taken up by the walls, which is very expensive. So when you turn to a building like this one, which has very thin walls, you've made a major saving. And it's done by having the outer wall not load-bearing at all. It's just hung on to the face of the structure. So this is the first example of what you would now call a curtain wall. The Unity building on the left introduces the first steel in Chicago on a large scale. And then from this point onwards, it goes on to making major steel framed skyscrapers. This one's a bit different from most though. This is again a portal frame. Look at the arches down in the section. It's actually a portal frame structure. And that's the Woolworth building in America gives rise to this building in Melbourne, which is known as Woolworth Gothic style, because it's the style favoured for the skyscraper. And the Empire State Building, finally in America. Wonderful scenes of this assembly. Here's the World Trade Center, now destroyed and under construction. Oh, and yes, right. Building. Now I'm going to go to the curtain wall, which is the point I just touched on before, so I got out of order. The idea of having a frame which has just a non-structural wall on the surface of it is a really important idea for the 20th century. It appears early in the 19th century in buildings like greenhouses. This is one where there's a really architectural effort made to design a wall which hung onto the face of the building. So you just had the frame and this cladding, which is just to keep the weather out, essentially, not to support the building at all. This was designed in Europe. And here now is the most famous example, the Menier chocolate factory in France. These developments sometimes have a sort of novelty element to them, and the idea of a chocolate factory has partly stimulated this novel design. The other thing was that this was a real factory that made chocolates. It had machinery, and the machinery was driven by water in the Noiselle, the river over which it spans. So it was built as a bridge with water wheels below it, turning the machinery, and on the bridge was this structure which had, instead of having load-bearing walls, had this iron framing with diagonals along it, which, if anything, was designed to deny the load in the wall. They actually designed to show that this is a non-load-bearing structure, highly ornamental design. You can see the turbines at the bottom which turn the machinery. So there it is. It's a purely surface treatment, a diagonal framing on the wall, and then packed with ornamental brick and tile afterwards to give that novel effect. Then the idea is taken up in department stores. It's long demolished one, which is why I haven't got a better picture. But this department store in Berlin, in which you have the whole street front in sheet glass to reveal the interior. And then, again in Germany, the idea of making the whole building like that, not just for show, but to make a whole building like that. So this is a very early curtain wall in 1903. Now, I don't know if anybody here is so uncool as to watch the Antiques Roadshow on television. I suppose nobody does, do they? Because if you do, almost every episode they come up with teddy bears. The most valuable teddy bear in the world is made by the Steiff Company, which is this company here. So this was the factory that made the famous Steiff teddy bears. And you can see the details of the wall, which is totally hung onto the face of the iron structure. And you can see that again it has extruded terracotta sections making the floor fireproof at that bottom part of the diagram. Now this is the building I meant to refer to before. This is the Monadnock building, which is the highest load-bearing brick building in Chicago, which became so high that you could hardly see through the windows at the bottom because the wall was so thick. And that's what gives way to the new curtain wall system and the Reliance building, which we just saw. Here now is how the Reliance building is built. You see the steel frame, then offered as these struts, which are supporting the bay on the outside, and glazed terracotta just hung onto the face. So at first sight, you think you're looking perhaps at a terracotta building, but it's just a facing hung onto the steel frame. And you end up with the modern Seagram building by Mies van der Rohe in New York in the mid-20th century, the epitome of the glass curtain wall and the ancestor of many more which are built since that time. And that's where I finish. Thank you.